Okay, thank you. Okay, one moment, I will point alarm. Okay. Okay. Okay, thank you very much. So my talk is a continuation of the previous talk and is devoted to consideration of some differential equation with singular perturbation and impulse in actions or impulse influence. Today we will consider two type of differential equation. The first order differential equation and the ordinary differential equation, and the second order partial differential equation, namely heat equation. Heat equation. Before the consideration of this equation, I would like to attract your attention to some, it seems to me, interesting facts or properties of impulsive systems. And later, I would like to describe in general boundary layer function methods and the Vichy-Christianic methods. These methods will be applied for construction of asymptotic solution for mentioned above equations. Sorry, can you give me a check, okay? Because I need for some explanation using this disk, okay? There is no check. Yes, sorry, I've not recognized at the moment, okay? So, here you can see the brief abstract of this part of talk, and I proceed to the next slides about brief history of impulse systems. As you can see, I would like to mention some paper by Anatoly Dmitrievich Meshkis and Anatoly Mikhailovich Samoylenko, who proposed in the beginning of 16th years of last centuries new approach for description of impulse systems, and consequently they develop new methods for consideration and studies of impulsive system. This direction was fruitfully developed in Kyiv scientific schools, especially at the Institute of Mathematics of National Academy of Science and Kyiv National University, named after Taras Shevchenko. A lot of young people, young PhD students studied different problems for impulsive systems, and maybe I know that many researchers from Kazakhstan also were involved in studies of this problem. So now a short. Okay, please next slide, because this device did not work at the present. Please give next slide. Okay. So here you can see the list of main problems that were studied for impulsive system. It is not full list of problem that was studied, because till now there are many works devoted to the elaboration of different methods and different topic of impulsive system. By the way, I can mention a problem connected with differential equation with delay or with the weighted arguments. So here you can see only a list of problems devoted to ordinary differential equation with usual standard or regular arguments, and also it is only a sketch of list of the problem that were studied before and are continuing studied at present. Okay. Okay, thank you very much. I keep some pause for you, your reading. Okay. Now I would like to explain the synthesis, mathematical synthesis of impulse action. In general, system with impulse actions has as this continuous condition. And condition of impulse action means that there are some moment of time at which the trajectory of a moving point, phase point, can instantly change the trajectory. They change from one trajectory to another trajectory. So we have some jump in general. Okay. We can consider, for example, for the second order differential equation, a continuous solution. In this case, we will have jump of first derivative or other derivative. It depends on kind of differential equation. So there is notation of this problem, and equation one we consider at the time except moment impulse action, and at time of moment at moment of impulse action the condition two works. So we have a difference before meaning of function before jump and after jump. So in the left side, it is delta function. It is not delta. The notation for Laplace operation is difference. The notation for difference. Okay, and I would like also to mention about two types of impulse action. We can consider impulse action at the fixed or given moment of time. In this case, the system is called impulse system with fixing moment of impulse action. There are different and kind of example can be mentioned for this situation. No, for example, you have some processes where at the given moment you have to put additional material to this system. It may be some biological, some economic model, maybe some other in technology, technologies process, and so on. Another problem is connected with consideration of system with impulse action at not fixed moment of time. A simplest example of such situation may be the jump of a ball. If you take ball and put him to fall on the table, you will see that after the first meeting with the table, the ball will go above, but the high of this ball will be less than at the previous stage. Later, he will attach another time this table and go right, go up again, but the height will be less, and so on. So we don't make describe the time of moment when this ball touch table, and a moment of meeting with table, we have a moment of impulse action. So it is the simplest example of system with impulse action and the non-fixed moment of time. You can also propose another example when impulse action is defined from some condition which contain some characteristic of considering the system or other problem or processes. But maybe it is the simplest example of such problem. Everybody can see, can observe such moving. So, of course, when we consider impulse action, impulse system, there arises a natural question: what notable properties of the system we have due to impulse action? impulse action. And so the impulse systems have a lot of interesting properties, I list only some of these interesting properties. It seems to me, first of all, I list and will give an example of properties connected with prolongation of solution. If you consider differential equation, you know that this differential equation, according to theorem of existence of solution, has solution at some interval. According to this theorem, this solution exists on the finite interval. But if you apply theorem about prolongation of equation, you will obtain the maximum interval of existence of solution. So I will consider later in the next slides some example of different order differential equation of first order when this maximum interval is finite, but due to impulse action, we obtain the infinite interval of existence of solution of such problem. The next problem is connected with existence or not the existence of solution of initial problem or boundary value problem. Due to impulse action, there are a problem when system has no solution with impulse action, despite that without impulse action, the system has solution. And opposite, in contrast, some system cannot solution without impulse action, but due to impulse action, the system has solution. Now, the next properties, change of stability of solution. As you know, the first book devoted to impulse system was published in Kyiv in 1978, it seems to me, or 88. There are here the amount of participants of the conference, there are a lot of experts in the fields, so I don't know remember the exact year when this book was published. It seems to me 19, later 7 or 8, but the last digital is 8. I know exactly, but later this book was translated into English, and English version of this book was published in 1895. This book was enlarged with new material, but I recall about this book because in the first book published in Kyiv, in first version, this book was written by Anatoly Mikhailovich Samonenko and Mykola Alexeyevich Prestyuk. One chapter was devoted to study of stability of solution, and in this chapter, it seems to me the chapter number 3, there are some examples which demonstrate change of stability of solutions. So, sorry. Sorry. Okay, and maybe in some sense new properties, but about these properties, many experts knew about these properties connected with coexistence of infinite number of periodic solutions with different periods, according to Sharkovsky order. Maybe you know that in one-dimensional dynamical system, the Sharkovsky theorem are well known, and it is distinguished achievement of Kyiv scientific schools. And in 1964, Sharkovsky published theorem, according to which, if some mapping of finite interval, for example, from 0 till 1, has this mapping, has periodic point of period 3, then this mapping has periodic point of any period. Later, it seems to me British science, York and Lee publish a paper maybe in 15 years later with title Period of 3 implying chaos. It is a very famous paper, and it seems to me that after this paper, the studies of connected with one-dimensional dynamical system were receiving new impulse, and many people studies this and develop this direction. I will present some example, but without calculation, without some details. You can find corresponding details in the paper published in Ukrainian Mathematical Journal. Okay, so the next sentences, which I consider very important, is the next, that due to condition of impulse actions, even a linear system became essentially non-linear system. It is this moment can be argued by different reasons, but the first reason is this is next. If you have linear system, you have some properties associated with linear system, but due to impulse action, you receive system which has some properties that can be not exist in linear system in general, in principle. So I proceed to consideration some example. The simple example connected with equation 5, you know that this equation has a solution as tangent function. It depends of initial condition. In this simple case, when initial case condition are trivial, you have exactly tangent function. Tangent function. And if you add to this equation sum additional condition of impulse action at a not fixed moment of time, you receive impulse system, and this impulse system has solution which define a maximum interval, and this maximum interval is infinite. At the same time, maximum interval for this function is known as finite. For solution with trivial initial condition. Okay, and another example can be connected with the consideration of equation number 7, and it related with periodic solution of linear equation, in general linear equation. If you write in the right side 0, we will have a linear system, and with consideration of impulse action in form 8, this impulse action, the impulse system can has a quasi-periodic solution. In this case, you will have a solution that is property of a linear system equation, and additional solution which is appear as solution of system with impulse action. So of course, usually it is obviously that some additional condition for values of impulse action and moment of and must be fulfilled. Okay, the next example. And finally, the set example connected with coexistence of infinite set of periodic solution with different periods. If we consider a well-known equation for harmonic oscillation, equation number 9, and we know that this equation has periodic solution with a period written on this slide. Under additional condition, condition 10, we can study a question about existence of periodic solution with these impulse systems. In this case, we must consider some mapping of real line inside. This mapping is right under equation 10, and so we consider some mapping and or one-dimensional system, dynamical system, and can apply some results related with Sharkovsky's theorem. In this case, due to correspondence choice of function of impulse action in the right side of 10, we can find such mapping when this mapping, such impulse action, that this mapping will have periodic point of period 3. So, according to Sharkovsky's theorem, we will have that impulse system 9 and 10 will have infinite number of periodic solution. This periodic solution with differ of number of point of discontinuous of the first derivative, and accordingly the numbers or number of impulse action during period. So this example demonstrates some properties that are very interesting of impulse action. Okay, now I would like to do some very brief remarks about study of impulse system with asymptotic methods, because later my attention I would like to attract your attention to system 12 under condition 1.2. No, some disconvenient of notation. So usually it is a tradition to recall about a paper by Lyubov-Krylov on 1973 in preface to the book by Mykola Perestyuk and Anatoly Samoylenko, Devoted to Impulse Systems. Yuri Alexeyevich Metropolsky mentioned this example and this paper about studying by mathematical method, asymptotic method by method of averaging, a mathematical model of clock mechanism. Later, at the beginning of 16 and it's 16 in the middle of 16 years, a lot of paper were devoted to the application of different methods, asymptotic methods, to consideration of impulse system with small perturbation. At the first step of such research, conditional impulse action, it was connected with system with impulse action at not fixed moment of time. This impulse action was changed into some condition, and this condition contain generalized function, Dirac function. Later, but this function was represented in the special trigonometric series, but this series was diverged in general. So it was diverged on some for a lot of points of real line, and later in the sequel, in another in paper of other people, members of Kiev Scientific School, first of all in Kiev, it was applied another approach where the asymptotic solution were constructed as discontinuous function with some correspondent properties obtained due to asymptotic methods. So then later we will consider equation 12 with impulse action at a fixed moment of time. Before consideration of this equation and application of these asymptotic methods to construction of asymptotic solution, I would like to attract your attention to function boundary layer function methods. Sometimes this method is called as Vasilyeva-Butuzov methods, or a similar, according to the similar titles. Okay, if we consider equation 12 and try to find asymptotic solution of equation 12 in the form of asymptotic series 13, we, after using of Taylor expansion for right side function in 12, we obtain the following relation. The last formulas, this slide. Later, according to the standard ideas of asymptotic methods, you will receive a set of the relation of one equation for determination of any terms of asymptotic solution. As you remember, yesterday I told you about application of regular or direct asymptotic expansion for regular perturbed differential equation. And I told you that in this case, we do splitting of nonlinear problem in a set of infinite set of linear problem. In contrast, this situation, in the case of singular equation, at the first step, we will have non-linear equation. It is difference between some difference between singular perturbed system and regular perturbed system for case of differential equation. Other equations are linear, and the next terms of asymptotic as asymptotic expansion, we obtain a solution of simple algebraic equation. In this case, we do only differentiation, operation of differentiation of the previous terms, the terms that we obtained at the previous steps, and we must divide for the derivatives of the function in right side of equation 12. So it must be usual or obvious restriction about function in the right side, and it's a solution for unperturbed system. So at the first equation, we have a function that implicitly defines some function. So in this case, we must recall a well-known theorem about existence of function, which define implicit function theorem. But if you recall this theorem, you know that this theorem give you only sufficient condition for existence of local solution of this equation. For this case, we need to have global solution of such equation. So we have also some result about global solution, and this topic of global implicit function theorem are actual till present, and many papers are devoted to this topic for different problem and with different application in different fields of mathematics. But because of some lack of time, I will not attract your attention to this problem, but I can give you some reference connected with these problems, and you can study, if you want, some result concerning or related this problem. So we can receive asymptotic solution for the given equation, but there is another problem. This asymptotic solution do not obligate to satisfy the initial condition, because this initial condition is connected. Initial condition for constructed solution is connected with functions that we define from implicit function relation number 1 in these slides. For to solve this problem, we apply another technique, and this technique is connected with boundary layer function, and this technique was applied for different and a lot of problems by Vishek, by Vasilyeva, Butuzo, and their pupils in very different problems. So to understand the main idea of these methods, we consider simple problem, a linear equation number 14. Under initial condition, the equation is very simple, and any students can obtain exact solution. Good relax, good for relax. Okay. Uh, it's suitable for me because I have some time for relaxation. Okay, good. So you can obtain a solution in the form of 15 or can write this solution in form, the next form. If you introduce so-called quick time, t minus t sub 0 divided by epsilon, in this case, you can represent the solution in special case. So, similar to equation, to function 15, we can construct asymptotic solution with using of this new variable time, a time variable. Okay. Now I will present some result about consideration of this equation number 1.1. I will say equation number 1 in sequel. So we consider equation of first order with singular perturbation. It is nonlinear equation. And we add conditional impulse action, condition number 2. Also, we do some assumption about moment and impulse action, because if this condition about difference between moment of impulse action will not fulfilled, in this case, we will have situation like a moving of ball when he fall on the table. Because in this case, the difference between moments of this between sequel moment of impulse will be shorter and shorter, and later in the limited in the limiting we will stop these processes at the limited point. So we suppose that problem under consideration for unperturbed problem number 3, 4, has bounded solution. It is some assumption because problem has a general form, and we want to construct a special solution, particular solutions, namely asymptotic solution. So for us, it is very important to start from point when the initial problem has a solution, and we can assume that it is a sense to construct some additional solution which be tends, this asymptotic solution will be tends to the solution of a problem without perturbation. Problem number 3, 4. Later, you see some additional assumption about function in right side of equation number 1. So you have some assumption about the first derivative. It is important because, as you see at the previous example, when we consider as asymptotic assumption for the ordinary differential equation without impulse action, and we try to apply direct asymptotic expansion, and later we introduce boundary layer of function. This some relation contain first derivative of the function in right side. So we suppose that this function is not equal to 0. Later, we suppose that this function and function of impulse action has infinite many derivatives, and derivatives of impulse action is not equal to 0, because this condition is needed for a solution sum system in the sequel. Now we consider the form of asymptotic solution. According to the concepts of asymptotic methods, we consider two problems in asymptotic methods in perturbation theory. First of all, we must to find the form of asymptotic solution, the first problem. Another problem, we must to develop algorithm for construction of asymptotic solution. And the third problem is we must justify the constructed asymptotic solution and propose algorithm. The last top point means that we must prove or find asymptotic estimation how exact is the constructed asymptotic solution. In the case when we consider some boundary or initial problem, or we have exact solution, we can suppose that we can obtain exact solution. In this case, we can consider difference between exact solution and constructed asymptotic solution. In other case, when we have no initial condition or we have no boundary condition, in this case, we consider some particular solution of the equation without any additional condition. In this case, we consider how this constructed notation satisfies this given equation. And we substitute this constructed solution into equation and try to evaluate the value, asymptotic value of the obtained values, obtained quantity. Okay, so as you as you've seen, we suggest to construct asymptotic solution in form number 5. This solution consists of the two parts. The first part is so-called regular part of asymptotic solution, and the second part is so-called singular part of asymptotic solution. It is solution that correspond to given equation, initial equation. So the regular part of solution is a solution of equation without impulse action, and singular part contains as part corresponding to solution with initial condition, and the most terms of this asymptotic singular part of asymptotic solution correspond to impulse action. So you can see that function px, here it is the notation of this function by two letters. The first function p sub 0 x and no, a moment. You have some in this representation contains some with respect to moment of impulse action, and every terms of boundary value function with singular part contains boundary value function. It corresponds to moment of singular part of asymptotics. So function pkx are defined for all index, and we can consider a solution in the positive direction of real line as well as in the negative direction of real line. So by standard approach of asymptotic methods, we substitute asymptotic equation, asymptotic solution number 5 into equation, and also in the moment of impulse action. In this case, we obtain the problem number 6, and as you see, the first equation, when epsilon is equal to epsilon contain 0 power, we obtain equation which define implicitly function x sub 0 with bar, and other terms, other equations are linear and contains give us possibility to find another terms of impulse of asymptotic expansion. So if we suppose that the first equation, implicit function relation, provide us with some solution, by the next relation equation, we can easily to calculate any terms of asymptotic solution of its regular part, So in this context, we can consider this problem is solved, because it is standard problem with consideration of ordinary differential equation, single perturbation under some initial condition. The main contents of these studies now is connected with construction of a singular part of asymptotics. In this case, we obtain some equation for every term of asymptotic expansion. We consider at this present this term for the first time of impulse action, and the first equation is nonlinear equation, and other equation are linear, non-homogeneous equation. Their non-homogeneous function in right side of equation number 7 can be calculated recurrently, is the first step or the first point of the research. And the next point is connected with calculation of initial data. So if we used some initial data for initial problem, in this case, by applying this initial condition for asymptotic solution, we obtain some initial condition for system 7 for singular terms for singular part of asymptotics. And this case related with the first moment of impulse action will be repeated at the next moment of impulse action. So it is the principle, it is the main, it is enough to understand the main idea what are used for calculation of any term of asymptotic equation. According what it is necessary to point about the first equation. The first equation is nonlinear, but as you can see, we can put the trivial solution of the first equation, because this equation is particular, this solution is particular solution of this nonlinear equation, and we construct not general solution of problem under consideration, we construct only particular solution. We need to construct only particular solution. So the last sentences on this slide is about that in such manner we can construct other terms of asymptotic solution. Any terms P sub kx also satisfy some system which are analog of system 7, 8, and we have the similar points, the similar problems, similar differential equation. So I will formulate some properties of function involved in the asymptotic expansion. First of all, function pkk is boundary layer function. It is proved in lemma 1.1, and the main result is about estimation of or justification of this asymptotic technique. So if we consider some finite interval, because on this finite interval we have only finite number of impulse action. And so if you consider some particular sum of asymptotic solution and consider difference between exact solution and this particular case and calculate maximum, we will obtain that this difference has order, asymptotic order, epsilon of epsilon in power n plus 1. So if we can to truncate this asymptotic expansion on n plus 1 terms, so the accuracy of asymptotic expansion is connected with this term that we take not into consideration. So in such manner, we can consider that we solved this problem. Another problem is connected with case when impulse action has a small perturbation. It is some particular case of this problem considering before, and In general, there is no some new or specific difficulties for consideration of this problem, but it has some synthesis for some problem. I will not discuss this topic or this problem in details, but you can see that we applying also the same form of asymptotic solution, number 5, and we uh, obtain the same properties, obtain similar, like just a little other condition for initial condition, and also we have that terms of singular part asymptotic are boundary layer function, and they satisfy estimation 4, and also this analog of theorem 1 is true for this case, Now it is next part of my topic. It is connected with application of Vishek-Lusternik methods to construction of asymptotic solution of heat differential equation with impulse action. So I will describe only in general the synthesis of Vishek-Lusternik methods. This method was proposed in the 15th year of last century, and it is, in some sense, popular because many paper deals with the application of these methods. The main idea of this method is the following: as if you consider some partial differential equation, you consider the solution to this equation in some boundaries. If you suppose that this some domain, if this domain is is fine in some sense, its boundary is smooth, so it is under some condition in the, for example, in the case of, in the case of constant coefficient, there are a lot of statements about existence of solution of such problem for given domain. Vishek, in the remark, Josipovich Vishek and Lusternik, he was a student of Vishek, proposed these methods for constructing of asymptotic solution for elliptic equation with singular perturbation. So they consider some elliptic equation with small parameters, the higher derivatives. No, elliptic equation, so Laplacian, so a small derivative near Laplacian. So I will tell you about main idea of this method. So if we consider a part of boundary of the domain D, so in this part, D epsilon, this part, we construct a solution according standard idea of elliptic theory, and in the part, this part, we apply an idea of boundary value function methods and construct some solutions according to the ideas of boundary value methods. Shortly, it is the main idea of Vishek-Lusternik approach. So we consider equation number 1. So, and the every values that involved in this problem are supposed to be represented as asymptotic equation. We consider general case. Additionally, we consider initial condition number 2, and boundary condition number 3, and condition of impulse action. We suppose that at some moment of time, denoted by T sub I, there are some jumps of solution in domain under consideration. We consider one-dimensional problem, so independent space variables vary on the interval from 0 till 1. equation, because equation we consider in this domain, in this interval, and other condition we consider including the boundary point. Okay. Um, before consideration, here is this, of course, is the result of consideration, previous consideration, not today. We do some assumption about values involved in this problem, and the main synthesis of this slide that we seek solution in the form number 5. Number 5. The bar U, function bar U, is regular part of asymptotics. It is constructed in a usual way, and the regular part contains many terms. In this case, you have 1, 2, 3, 4, and additionally a boundary layer function. So we consider the following function. So in neighborhood of point 0 and similarly point 1, we consider function, boundary value function in direction of time variable. We consider boundary layer function in direction of space variable. We also consider additional boundary value function in the corner of near the point 0. It is additional terms of asymptotic expansion, as well as additional terms of asymptotic expansion connected with x variable. And other terms of asymptotic expansion is similar to terms of asymptotic equation of previous problems. We have a boundary layer function PGU and some additional function connected with some additional correlation terms connected with corner point. So there's a lot of slides, and maybe difficult to see or to write, to read these slides now. I will not in details consider these slides. I will show only some results, some statement about properties. So this problem is solved in details, and after some description of the problem, we obtain that the initial terms of singular part asymptotic is a boundary layer function. Later, we consider equation for any terms of asymptotical solution. It is some tedious formula. So it seems to me, on my point of view, it is not very interesting to consider every equation at this point. So the next steps, the next point that other function also are boundary layer function statement of this statement lemma. Okay, the next lemma, it is also problems. The statement of layer about that constructed function is boundary layer function, and now you can consider angle function, and this angle function also are boundary layer function. It is the synthesis of this lemma. Next, we have some assumption, and we have also the statement about this function involves 5 minutes I have. Okay. Also a boundary value function, the first row of this slide, and the same statement for other terms of, we have 4, 5, we have some 7 terms of asymptotic expansion. And lemma 7 and lemma 8. 8 lemma about this, any points of asymptotic equation is boundary layer functions. So the main statements that difference between exact solution and asymptotic approximation have asymptotics order of n plus 1. Okay, thank you very much. Не рассматривалось. Да. А если в правой части дела, ну, я должен отвечать, я могу отвечать по-русски или как? Да. Can you, I have some participants from Germany, so I will try to reply to your question. So, you asking you about including Dirac function into the equation for determination of asymptotic solution. If you consider some equation with presence of Dirac function, generalized function, there is a natural question. In what sense you will consider this solution? You must consider, you have considered this equation in generalized sense. So you can construct only formal solution, but what this formal solution will can do for application, I don't know really. So it is better to construct discontinuous solution, because this discontinuous solution will give you smooth solution for the any time except moment of impulse action, and for the moment of impulse action, this short instance influence, and this moment can be considered separately, maybe. Okay, I will give you answer. Maybe we discuss this problem later after my talk. Okay. Yeah. Okay. Okay. What? Okay. 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 Yes. Okay. And what about the function? No, you take from the space C infinity. Okay. Okay. I will answer your question. So, coefficient of equation number 1, as well as function in the right side and initial function and functional initial condition are supposed to be infinitely differentiable. It is necessary if you want to construct asymptotic solution of any order. If the order of asymptotic solution will be arbitrary, you don't know how much you need smoothness of this solution. If you construct only 1, 2, or 3, it is sufficient to have finite correspondingly three derivative. It is sufficient. It is this condition is appear due to technology, technique of construction of asymptotic solution. We need to expand right side and moment of impulse action in corresponding Taylor function, in Taylor expansion. In this case, you need to have so much derivative as you need.
Today I continue my lectures. The second lecture, I want to start by reminding you a bit what was on the first lecture. It was definition of tangential derivatives, and in particular, definition of the hypersurface, definition of Günther's derivatives, which are tangential derivatives, and definition of Stokes derivatives. Let us start by the definition of hypersurfaces. Oh, sorry. Again, a mistake. Yes. Definition of hypersurface is this one here, the first line. It is defined by with the help of the function as zero or certain function which has non-zero gradient. And the gradient of this function defines the normal vector orthogonal to the surface. It's in the last line here. Again, I am mistaken. Sorry. Oh. Sorry. Where I am now. Lecture 2. Yes. Here we have the definition of the normal vector field here as the normalized gradient of the generating function of the surface. Okay, now we have the hypersurface, we have normal vector field, and next we here is some picture surface with the normal vector. You see it, and here is a definition of Günther's derivatives. It is projection of coordinate derivatives on this surface. So we subtract from the coordinate derivatives the normal derivative multiplied by the component of the normal vector, and we'll get a projection of the coordinate derivatives to the surface, and it is tangent derivative of Günther, and the tangent derivative is of Stokes is next. Well, and they play important role in our exposition. Okay. Next we have what we have defined yesterday. It is the gradient, which is defined in a different way, the classical differential geometry. Gradient on the surface gradient and surface divergence are defined as with the help of the Günther's derivatives. so you don't need much effort to write them. If you know the classical gradient, you just replace the classical derivatives, I mean the coordinate derivatives by Günther's derivatives, and you get the gradient on the surface. Same with divergence, and same with the Laplace-Beltrami operator, which is the sum of squares of Günther's derivatives. So for lazy mathematician, it's a good news, because you don't need to remember much to write those operators on the surface. Sorry, it's maybe not a very good joke. Now lemma. In this lemma, I collected some important properties of the Günther's and Stokes derivatives. First of them is about a very trivial property of the Stokes derivatives. Then with the same index mgg, they are zero, of course, because it comes from the definition just. The second property, mgk is minus mgk, is also a very simple consequence of the definition. But the next one is important because you have representation of coordinate derivatives with the help of Stokes derivatives. How you can write, for example, you have the differential operator and you want to understand, can you consider it on the surface? So you rewrite it in Stokes derivatives, or you rewrite it in Günther's derivatives also. For the Günther's derivatives, we have also a formula how to rewrite it. No, well, it's easy actually. Günther's derivatives. Sorry, I have not written, I think, it here. Well, but it's very easy because the Günther's derivative is the coordinate derivative minus nu g then nu. So nu g then you put on another side, you will get that the coordinate derivative is the Günther's derivative plus nu g then nu. You rewrite your differential operator in this form, in the form of in terms of Günther's or Stokes derivatives, and if there does not appear normal derivative, that means that it is tangent derivative, and you can consider it on the surface. Also, it's important that the Günther's derivatives can be expressed with the help of Stokes derivatives, and the Stokes derivatives can be expressed also Günther's derivatives. So everything can be rewritten in all these three derivatives. I mean, it's three systems of derivatives. Well, and the property 6, it shows you that the Günther's derivatives are linearly dependent. Multiplied by the normal vector field, the Günther's derivatives, I mean the scalar product with of the gradient of Günther's derivative, multiplied by the normal vector is 0. Well, nevertheless, you cannot drop any component of these Günther's derivatives, because the Laplace-Beltrami operator, you cannot write it in the right form. It's the sum of squares of all these derivatives. But they are linearly dependent, and one should be very careful with this. Okay. Also, the Stokes derivatives are also linearly dependent. You see here in the 7, of course, that with the help of permutation sign, the sum gives you 0. Here is the commutator of Günther's derivatives. Of course, the coordinate derivatives commute without problem. The commutant is always 0, but with Günther's derivatives, one should be careful. The commutant is some operator, Well, it's written here how to commute them. Also, derivative of normal vector field, derivative with the coordinate derivatives of the normals, the components of the normal vector field coincides with derivatives with the Günther's tangential differential operators. They coincide. Why? Because normal derivative of the normal vector field is zero. Normal derivative of normal vector field is zero. That's why these two derivatives coincide. Now about spaces on the hypersurface. You can define here general Bessel potential space, Sobolev-Slobodetsky space, but these definitions are a bit involved and I don't expose it here. But to define the Sobolev space, it's easy. The definition is as in a classical case, in Rn, you take derivatives for Sobolev space WPM, you take all Günther's derivatives, mixed type Günther's derivatives up to order M, and well, you will get, and if these all derivatives up to order M belong to LP space, then you can be sure that this function belongs to the Sobolev space WPM. Okay, the norm, of course, is defined in natural way. All these derivatives, we take LP norm. Sorry, as always. Yes, here is the definition of the Sobolev space. Here was the definition of permutation index, with the help of which we see that the Stokes derivatives are linearly dependent, and the commutants are exposed here of the differential operators. Yes. And here the definition of Sobolev spaces, and here is the norm of defined in Sobolev space. Norm, of course, is in a natural way. You take the norm of all derivatives and take sum and then square, not square root, but the, well, special root from this sum. Okay, it's nothing new, classical definition, but with Günther's derivatives. And in P is equal to, in the case P is equal to, as always, we have, of course, the Hilbert space. Hilbert space, where the scalar product is defined in the last line. And so Sobolev space W2M is a Hilbert space. Okay. Now, yes, I told you the definition. We skipped the definition of the Sobolev of Bessel potential and Sobolev-Slobodetsky spaces. Well, consider that as interpolation of between the Sobolev spaces. With two different methods, you will get, in one case, you will get Sobolev-Slobodetsky spaces. In another case, you get Bessel potential spaces, but for the integer M, they all coincide. Okay. Next, we will speak about covariant derivatives and curvatures. Covariant derivative on the surface, we have, together with tangential derivatives, we have covariant derivatives. What is covariant derivative? Derivative is covariant if the derivative of the vector, if the vector was tangential to the surface. After taking derivative, it will remain tangential. Then the derivative is called covariant. Definition of covariant derivative from the classical differential geometry is with the help of a bit complicated. I will expose it on the next slide, but easy way to define the covariant derivative is to take just the projection. So Günther's derivatives, for example, if you take the vector of, the gradient of Günther's derivative from the function, it is tangential. But if you take the Günther's derivatives, each Günther derivative is not tangential. So you have to apply the projection operator to Günther's derivative to make it covariant derivative. And if you in classical geometry, the covariant derivatives are defined in a different way with the help of Christoffel symbol, which plays an important role not only in defining the covariant derivatives, but in the whole differential geometry. The Christoffel symbols are exposed here. You see the first formula on the slide. It's a Christoffel symbol. You take the metric tensor, a covariant and contravariant metric tensor, and with the help of deriving the covariant and multiplied by the contravariant tensor, and a lot of those constants, you get these constants of Christoffel symbol, not constants, sorry, they are functions. They vary from point to point. You get the Christoffel symbols, rather complicated. And covariant derivatives are exposed here, you see. It's a combination of the derivatives with the Christoffel symbols in the formula. Yeah. Again. Here, you see, these are, well, definition of the covariant derivatives. But we go with the simple way. We just take the projection. Okay. From the coefficients in the remainder, we construct, not we, but R is constructed very important metrics. It is the Weingarten matrix. Weingarten matrix is the source for three very important, not constants, curvatures. First of all, principal curvatures, they are the eigenvalues of this matrix, Weingarten matrix. Also, the tensor, mean curvature is the trace. The trace, the sum of the diagonal elements. It's the mean curvature, or it's the same as the sum of the eigenvalues, is the mean curvature. And the determinant is the Gaussian curvature. So, as you see, the Weingarten matrix carries three different curvatures. It's very important. Weingarten matrix, the representation of Weingarten matrix depends, of course, on the system of vectors which you choose. System of course, the basis which you choose. And if you choose as a basis the projections of basic basis in Rn, compiled of zeros and one, EGs. If you choose their projections, we denote it by DG. The Weingarten matrix has a very simple form. It is just derivatives. Weingarten matrix consists DG nu K. It means Weingarten matrix consists of derivatives of the components of the normal. So it's very simple matrix in this representation, but it has one deficiency. The deficiency is that this matrix is not anymore, it's symmetric, but determinant is 0. So Gaussian curvature is not anymore the determinant. Also, eigenvalues are the same plus one more eigenvalue, 0. It becomes n by n, yes, n by n. In the classical Weingarten matrix is n minus 1 by n minus 1. In this case, it is n by n, and it contains eigenvalue 0. So the mean curvature is the same, sum of the, trace of this matrix. But the Gaussian curvature is different. Gaussian curvature, you cannot define as a determinant, but you can define as a product of eigenvalues. And then everything is okay. Yes. So now we have this Weingarten matrix, simple form. And yes, it's here. Yes, Weingarten matrix is the derivative of the normal components. It's symmetric and everything is okay. And here is the mean curvature you see. It's a product of eigenvalues. Deformation tensor. Deformation tensor we need to write equation which describes the formation of surfaces. It's not the shell theory still, but the next lecture I will speak about shells. And now just what we derived with my colleagues, Marius and Dorina Mitria. We derived first, it was long ago, almost, I think it's a bit more than 10 years ago, we derived the equation of the elastic surface. And this derivation is based on this deformation tensor. What is deformation tensor? Deformation tensor represents symmetrized covariant derivatives. So you take covariant derivative from U multiplied by another vector W, and then take plus covariant derivative of by W of the U multiplied by, sorry. There. Yes, it's something mixed here. Just a moment. Is it? It's not exposed still. It's symmetrized derivatives. Derivative dv of uw dw uv. Yes. No, I think it's correct. And why not covariant derivative in the first line, and why the covariant derivative in the second line? Because it's multiplied by the tangent vector. So you write here covariant derivative or usual derivative is the same. It becomes covariant because the projection applies automatically. So this is deformation tensor. Okay. And now the theorem. Deformation tensor, well, it's written here, deformation tensor in classical representation with the help of gammas. And now theorem states that the deformation matrix with Günther's derivatives acquires this form here. You can rewrite the deformation tensor just in terms of the Günther's derivatives, and then there appears derivatives of normal component, derivatives of normal components, or it just symmetrized derivatives by the covariant derivatives by the Günther's operators, Günther's tangential operators. As in classical case, dg uk plus dk ug. Here is the same, but with covariant Günther's derivatives. Okay. The surface Lamé operator. To derive surface Lamé operator, we follow the model which was suggested by Coiter. Well, in mechanics, it's so, in mathematical physics, that the equations are derived as the equations which minimizes certain energy forms. In this case, energy form is written here, integral from T, matrix T applied to gradient of the vector field, and not matrix, sorry, it's tensor, and multiplied by gradient of vector field. Well, here multiplication is the tensor, sense of tensor. The tensor T is consists of constant coefficients. In anisotropic case, well, it can also depend on X, but it's more complicated, which have these symmetries written here. In the case of isotropic case, it simplifies and is combination of two constants, Lamé constants, lambda and mu. But well, this energy functional, we find we derived its minimizer equation, solution of which minimizes this this expression, and it turned out that the Lamé operator, I mean the operator equation, which minimizes this energy functional, looks like as in formula 14. Or rewritten in different form, in formula 15, you see here a very classical expression of the Lamé operator in Rn. But the difference is this: we have here Laplace-Beltrami operator with projection. Then we have, again, gradient and divergence, as in classical case. And we have here mean curvature and the Weingarten matrix. The first two summands, if you consider the instead of the Günther's derivatives, consider the usual derivatives, it coincides with Lamé operator in Rn. But the last summand is different. But this last summand disappears, and here appear all the classical derivatives as soon as you have the flat case. Then the curvature is zero, and Günther's derivative coincide with the usual coordinate derivative. So it's a generalization, not generalization, but this form it acquires when you have this surface. So the equation is derived. Then we studied its properties and so on and so on. Killing's vector fields. Killing's vector fields are very important because by two reasons. First of all, what is Killing's vector field? When you have vector fields and you find the flows which correspond to these vector fields, distance to these points of the flows when they are Killing's vector fields does not change. They are constant. And the second reason is that they are solutions of homogeneous Lamé equation on the surface and on Rn. On this surface, it's of course rather complicated, and no solution still exists of it, and nobody studied deep the properties of this Killing's vector fields. But in Iran, they are known, I think, from 19th century, and they are they have very nice form. I will show it to you. Well, Killing's vector fields. Okay. Here. Yes, here it starts when we have a case of Rn, when the omega is Rn, then Killing's vector field is just has just a form A plus Bx. Well, not in Rn, it has such a form. X plus Bx, where B is the matrix represented here. It's skew symmetric. The dual matrix is minus the same matrix, but well, it's exposed here. In the three-dimensional case, it's much easier. It is defined by one vector and has the form which you see here. Yes, this form it has 3 by 3 matrix, which consists of elements of one vector, and a very nice form. And this is Killing's vector field, and or rigid motion. Killing's vector fields, they are called when we are on the surface normally, but in Rn, they are called rigid motions. Why rigid? When you move along these lines, your distances does not change. And they are solutions of Lamé equations. Lamé equation, homogeneous Lamé equation, zeros of Lamé equation. And Lamé equation has only these zeros, nothing more. Same happens on the surface. On the surface. Same happens on the surface. The linear space of Killing's vector fields on a surface, on a domain, coincides with the kernel of Lamé operator. So you see that these Killing's vector fields are important to know the zeros of Lamé equation. And well, it is also important because if you want to solve the Lamé equation on the surface, on the right-hand side, it has unique solution if the right-hand side, well, if you remove these zeros, I mean, take factor of vector fields, Killing's vector fields, on the right-hand side should be orthogonal to this all Killing's vector fields. Then you have the solvability of such equations. Well, they have also very important properties, these Killing's vector fields. We call some set of finite set called essentially m-dimensional if there exists m plus 1 point such that the difference between these any 2 points are linearly independent vectors. Linearly independent vectors. And if the Killing vector field vanishes on the essentially m-dimensional points set, n-1 dimensional set of points, then it is identically zero. You don't need to check it everywhere. That Killing's vector field is zero. You just need to check it in n-1 dimensional set of points which are linearly independent. I mean, the differences. Okay. And especially if it vanishes on the set which has non-zero measure, it disappears. It vanishes because you always find in such a set of non-zero measure, always find such a subset of essentially m-dimensional, n-1 dimensional points. Okay. Lyons-Lemaitre-Connes inequalities. Okay. What is the topic of this? Sorry, I have to control the time. I have 25 minutes, yes. Thank you. Okay. Solar space has dual space, of course. And the dual space is the space of generalized functions, distributions. And they are defined, they can be defined as dual space to solar W minus M is a dual space to WM. Or you can define it as a derivatives of LP M times. You take LP functions, take derivative of M times, it's some distribution, and then the W minus MP consists of those functions. Okay, why we need it? Well, embedding also, WM is embedded in LP, and LP embedded in W minus M. This embedding is even compact. Well, when we have open surface, open surface with boundary, then we can define W tilde. Oh, what happens? W tilde, which are roughly speaking, the functions which vanish on the boundary. Vanish on the boundary, or closure of the functions which are supported only inside. And W without tilde is a space which are restrictions of WPM functions on this subset of open with boundary. As usual, as it's always accepted, this notation. Oh, yes, here is the theorem about what? This theorem was proved by Lyons in P is equal to case, and here it's proved for any P, and it's proved also for WPM. What is the content of those theorems? I will explain it in words. If you have the functions which together function and its derivative belong to W minus 1, then the function belongs to LP. If the function and the M times derivatives belong to and M times derivatives belong to the WM, it is general also, it's for Bessel potential spaces, but let us speak about solar space. Function has derivative, and the function and all its derivatives up to the order M belong to W minus M, then function belongs to LP. It's important in considering the equations, and it yes. And the Korn's inequality states that you can introduce a norm with the help of deformation tensor, and it is equivalent norm. And this norm is equivalent to the original norm, although it takes much less derivatives, because in WPM you need all derivatives up to order m. But here, this due to symmetries, you have less derivatives, and it's surprising, but the space, the norm is equivalent even with this less derivatives if you take derivatives with the help of deformation tensor. It's also generalization of the lemma, which was proved by Searle. And now the last theorem in this section, it is surface Lamé operator is positive definite modulo Killing's vector fields. If you take factor with Killing's vector fields, the Lamé operator becomes positive definite on the surface, I mean. Combined with the Korn's inequality, well, it's written here, this inequality, and Lamé equation has only a finite number of linearly independent solutions, which are Killing's vector fields, what I promised. That Killing's vector fields play an important role in Lamé equation. They are zeros of Lamé equation, and nothing more, only they are zeros of the Lamé equation. And for the solubility of Lamé equation, you need that this right-hand side should be orthogonal to all Killing's vector fields. Okay. Now we start a new topic. And this new topic is connected with the derivation of the new equation for shell, which we have performed with my colleague Tengiz Buchupuri. We derived the shell equation with the help of Günther's derivatives and the gamma convergence. Here is what is, let us speak about gamma convergence. Sometimes it don't work to switch it. Next page. Oh, yes. Ennio De Giorgi was the first who introduced in 75 so-called gamma convergence. Italian mathematician, worked in calculus of variation, minimal surfaces, geometric measure theory, gamma convergence. Okay, definition. What is a gamma convergence? You have functions or functionals. It's almost the same. And we say that TGX gamma converges to T if for any sequence xg, TGXG is evaluated from below by Tx, limit of xg. X is limit of xg. So it's always for any subsequence, it's evaluated from below. But there exists one sequence, xg's, that TGXG converges to Tx. So it's called the recovery sequence. Recovery sequence. If you understand what is the essence of problems of mathematical physics, you understand that this definition is very important from the point of view of the problems of mathematical physics. Why? Because the mathematical physics, I mentioned it once, equations are derived as the minimizing certain energy integrals. So minimizing certain, it's functional. So minimizing this functional, you get the, if you have the convergence of some, for example, what is shell theory, how they are derived? You have some thin structure, you have the Lamé equation there in this thin structure. Then you send this thickness to 0, you get surface. And what type of convergence is correct convergence to derive the limit equation? This correct convergence is gamma convergence. Why? Because during the gamma convergence, you maintain the minimum of this functional. If functional at each index has minimum, these minimums converge to minimum of the limit functional. So it's ideal for deriving gamma convergence. This was noted by James. Oh, this was noted in applied to derive the equations for plates when we have not had carved thin structure, but we have thick plate. If you send the thickness of plate to 0, you derive Mueller, James, and third family, I forget. You derive the equation of the plate. And we, using this Günther's derivatives, applying the Günther's derivative, derived this equation for the carved structures. Okay, this will be the next, but now strange properties of gamma convergence. They are very strange, really. Because, for example, gamma convergence, it's very different from pointwise convergence. In the first example, the example is written here. Functions converge pointwise to 0, but gamma limit is different. It's written on the last formula, gamma limit. It's 0 and 1, not completely 0. So they are different. Another example shows that gamma limit is sensitive to multiplication and to sum. If you take function and multiply it, sequence and multiply it with minus, take minus function, the gamma limits will be different. If you take sum also, the gamma limit also will not be the limit of sum of the limits. That pointwise convergence has this property, that the limit of sum is the sum of limits, and the limit of multiplication by constants is the constant multiplied by the limit. The third strange property, the pointwise gamma limit exists and is different at every point. Pointwise and gamma limits exist and are different at every point, not in only one point as it was in the first example, but every point. Is this content of this example. Fourth example. Fifth example, there exists pointwise converging subsequence of the functions, but the gamma limit does not exist, and vice versa. The gamma limit exists and pointwise limit does not exist. Well, as you see, it's a totally different things. Okay, today I stop here. Thank you for your attention. Here is my mail. If somebody wants to get more detailed manuscript about those, about this, what I am telling here, you send me mail and I will reply with this manuscript. Thank you.
Can you show us the remaining slides?
Pardon?
Can you show us the remaining slides?
Remaining slides. Remaining slides, what do you mean? How many they are, or?
Some examples.
So about shells now, we will start here. Shells. Ah, I'm listing it for myself. Sorry. Forget that it's not connected. I am sorry that I don't speak at all. These examples, I was speaking about examples and does not switch it. Here is the Georges, and then the first example when the convergence don't coincide in at one point. Then the examples when they don't coincide, these gamma limits don't coincide in multiplied by constant, you get different. Taking sum, you get different limit. And also when the gamma limits are different at every point with this, compared to the pointwise limits, and the last two examples, they show that they are totally different. Exists gamma limit, does not exist pointwise limit, and vice versa. Okay, that's mail. Very easy mail. First three letters from my name and family name, and then gmail.com. And here I will speak about shells, which is a same structure, and then we will send the thickness of this same structure to 0 and try to derive what the limit equation will be with the help of gamma converters. Okay, then, well, these all Sobolev and other mathematicians.
This is your third lecture. Tomorrow's lecture.
We wanted slides of this lecture, not of the next
Pardon?
one. We wanted slides of this lecture, not of the following one.
Yeah.
Slides of T.
This is your next lecture. Right?
Next slide. One slide.
Это следующая ваша презентация. Третья лекция.
Не понял.
Это третья лекция, вы показываете нам, которую вы должны докладывать завтра.
А завтра вот с этого начнем.
Да, мы сейчас вам это показываем.
You wanted just the first page of this slide, which I will show
The
tomorrow.
last page of the next slide.
Yes. Yeah, first we will derive heat equation. I mean, when you have Laplace equation in the same structure, and then send this thickness to 0, what you will get in the limit? You will get the Laplace parameter. But in the case of Lamé equation, it's much difficult because you have system of equation, matrix operators, and then the limit is different. It's much more involved to calculate the limit in the case of Lamé operator. I answered your question. Thank you.
Is the gamma limit always unique?
Pardon?
Is the gamma limit unique? It's just
Gamma convergence. Is it unique
Gamma
or
convergence что?
единственное?
Единственность. Uniqueness of gamma convergence. What do you mean by uniqueness?
if the gamma limit exists.
Well, if it exists,
Is it just one?
If it exists, it's unique.
Okay, thank you.
Otherwise cannot be. Because it's minimizing the function.
Yes. I have to ask one question about Laplace operator.
Yes.
Integral derivatives.
Laplace parameter.
Yeah. Are there any results about the spectral properties of this operator? Spectral properties. Spectral.
Spectral
Yeah,
properties. Spectral properties. Not exactly. No. I think, well, special spectral properties of Laplace Beltrami operate on the surface. I don't know the investigations in this direction. We have, well, it is much easier. We have proved the unique solvability of such conditions for the unique solvability of those equations, which is important for us for the problems. But the spectral properties, you mean the spectral, the eigenvalues and so on, is much more involved than. No, I don't know the results.
Thank you. Then next, again. We are finished. Go hard break. Now, hard break. And we will continue
And the second lecture will give very bold holiday. He would speak in G-type critical exponents to the parabolic problem, history, new results, and open questions. Very bold represents Almaty.
Yeah, thank you.
Okay.
Thank you, Roland, for the nice introduction. Today we will continue our yesterday's lecture. Yesterday we give some historical information about the semilinear parabolic equation, including Fujita type critical exponents, about global existence and blow up of solutions. For the new participants, maybe I will remember some crucial results of yesterday's lecture. Yeah, the main results of today's presentation, based on our paper published in 2022 with my former PhD student Meirhan Burikhanov. And let us repeat yesterday's talk. Let us consider the following semilinear parabolic equation with power law nonlinearity on the right-hand side, given on the whole Euclidean space with non-negative Cauchy data. And it's known that there exists a local in time solution for suitable smooth initial data. For example, if you consider on the space of a continuous function, U0 should be from the C0 with compact support. Then there exists unique classical solution for some small time. And this time can be extended up to the maximal time, and this maximal time can be equal to infinity. In this case, we call that the solution exists globally. Or if this maximal time is bounded, then we say that the solution exists only up to this time. And if time goes to this T max, capital T max, then the solution goes to infinity. This phenomenon we call the blow up phenomenon, infinite time. Yeah, and also this problem was considered by Hiroshi Fujita, Japanese mathematician, in 1966, and he shows that if this power of u between 1 and 1 plus 2 divided by n, then there is no global in time positive solution. And if p greater than this number, 1 plus 2 divided by n. Therefore, sufficiently small initial data, there exists a global in time positive solution. And the critical case was later was proved by also Japanese mathematicians in two-dimensional case by Hayakawa and multi-dimensional case by Kobayashi, Shirao, Tanaka, and they prove that this case also there is no global in time non-negative solution, global solution. And this number is said critical Fujita type critical exponent or critical exponent in the sense of Fujita. And today, let us discuss about some non-local extensions of these results and also results about semilinear heat equation with a forcing term. And first, let us start with the non-local extensions. In 1969, Nagasawa Shirao considered the non-local space non-local extension of Fujita's results. They replaced Laplace operator by the fractional power of Laplace operator. Here, beta between 0 and 1, and they consider this kind of fractional heat equation. And they prove that the Fujita type critical exponent of this problem will be this number, 1 plus 2 beta divided by n. If beta goes to 1, then this critical exponent coincides with the classical Fujita critical exponent. And here we note that this critical exponent of the fractional case is less than the classical Fujita critical exponent. And later, also the Nagasawa Shirao proved only supercritical and subcritical case. And the critical case was proven by Sugitane in 1965. And later, Gueda and Kiran, they consider more general case and they also get the same results. Here, maybe I should mention, Mohtar Kiran was my second supervisor in my PhD. And I start learn this kind of problems thanks to him. Later, in 1998, a French mathematician, Philippe Souplet, considered this kind of non-local version of Fujita's problem. He considered non-local source term. The integral depends on the time. And he proves that in this case, Fujita critical exponent equals to infinity. It means that there is no global in-time solution for any p. And later, also, Philippe Souplet considered this kind of version of Fujita's problem. Here, in non-local source, we see some load term. And also in this case, Souplet proves that the critical exponent will be equals to infinity. That is, in this case, also, there is no global in time positive solution of this problem. His papers was published in 1998 in Siam Journal of Mathematical Analysis and the Journal of Differential Equations in 1999. And motivated by this paper, Terry Kadinavi, Flavio Dickstein, and Fred Weissler, they consider this kind of extension of Fujita's problem. Here, they put a more general time-dependent operator, integral operator, and they prove that there is another type of critical exponent. And they found this kind of critical exponent here, this value maximum of 1 divided by gamma, or 1 plus 2 minus gamma divided by n minus 2 plus 2 gamma. And if gamma goes to 0, then this results coincides with the results by Philippe Souplet. And they prove that if initial data is non-negative, and P satisfies this inequality, then there is no global in time positive solution. And also, if P greater than this number, maximum of these numbers, then also the similarity with the Fujita's result for sufficiently small initial data, the considered problem has a global in time positive solution. And their results was published in 2008 in the Journal of Nonlinear Analysis. And later, Fino and Kiran, they consider space fractional case of the same problem. And they also found the critical exponent like this. Here, the space order of fractional Laplacian is also here in the critical exponent. That is, the critical exponent in this case depends on the power of fractional Laplacian and also power of integral operator. And yeah, they also have the same results as a Cazenave-Dickstein-Whistler. And in 2005, Kiran, Laskray, and Tatar, they consider time fractional case of heat equation. Here, the alpha means fractional Caputo derivative. Here, I will write the definition of this operator. P minus S power minus alpha. And here, B U V S. And alpha between 0 and 1. Yeah, this operator calls Caputo fractional derivative. It was first time introduced by Italian mathematician, not mathematician, Italian physician, Michel Caputo. And they consider this kind of perturbation of Fujita's problem. And they found this kind of number. And they prove that if P less than this number, then there is no global in time positive solution. But later, Chinese mathematician Zhang and Sun, they consider the same problem as the Kiran and Laskray Tatar. And they improved the above results. They proved that here, this exponent depends on the alpha. But they proved that the critical exponent does not depend on the time fractional derivative. Mainly, they prove this kind of results. If P greater than 1 plus 2 divided by n, this is the same critical exponent as the Fujita, then there is then the solution exists globally for sufficiently small initial data. In the subcritical case, there is no global in time solution. But surprisingly, here, if you note, the critical case belongs to the global existence case. The Fujita's result, this case was about blow up. And also, this exponent greater than this one. And the more general case of these results later was obtained by Italian mathematician Dabico, Ebert, Picon in 2019, and also Zhang and Li. They also consider time fractional version of Cazenave-Dickstein-Whistler problem. Okay, now let us consider this kind of perturbation of Fujita's problem. Here, first term ut, but in the second term there is some fractional power of time derivative. But here, this is the alpha. It's another time fractional derivative in the sense of Riemann-Liouville. They're the same, but only the derivative will be outside of this integral. this kind of problem. And it was first time considered by De Andrade Viana. This is Brazilian mathematicians. They prove that the global existence results if P is subcritical and critical case. The critical exponent defined by this one. And later in our paper with Burhanov, we prove the blow-up results for the subcritical case. And here, critical exponent depends on the order of fractional derivative. If alpha goes to 1, then our critical exponent coincides with the Fujita critical exponent classical. But if alpha goes to 0, then the critical exponent will be the infinite. It means that if we put 0 here, then it will be just a first-time derivative by time. Then in this case, we get some Sobolev type equation. Then for Sobolev type equation, the critical exponent will be equal to infinity. It means that the Sobolev type equation don't have a global in time solution for any P. Okay, then, yeah, in 2000, Katerina Bendel and Howard Levine, Keith Jan, they consider another type of perturbation of Fujita's problem. They consider the same equation, but with this kind of forcing term depending only on the x, on the space variable. And they show that if integral of this forcing term is strictly positive, and the initial data is also non-negative, and if P between 1 and PS, here PS in 1 2-dimensional case, it's infinity. And started with 3-dimensional case, it can be defined by n divided by n minus 2. And in this case, the considered problem, the solution of considered problem blows up in finite time. Okay, it means that in 1-dimensional, 2-dimensional case, there is no global in time solution for any P. The critical exponents, they arise only started with 3-dimensional case. And yeah, critical case, in the critical case, they assuming this kind of restrictions for forcing term. They assume that the integral strictly positive, and this forcing term has this kind of asymptotically representation for sufficiently large x. And also they assume that U is non-negative, and the forcing term satisfies this kind of relation. By this assumption, the considered problem also don't have global in time positive solution. And if P greater than this number, if n started with 3-dimensional case, then there exists a sufficiently small U0 and a forcing term such that the problem admits global in time solution. And if integral of this forcing term is strictly negative, so for any P, there exists initial data U0 and the forcing theorem such that the solution of this problem exists globally. Yeah, but I should mention one open question related to this problem. When the integral of this function forcing term equal to 0, but the function is non-zero, then in this case still open the question about critical exponents or some blow-up results. And yeah, a little bit earlier, the same problem was considered by Jan in 1999, at the same time with Rospinsky. Is also published in 1999. And they considered this kind of positive forcing term bounded from above by this kind of polynomial. In this case, the critical exponent also will be the same. And in 2010, Kobayashi considered this kind of perturbation of Bendel-Levine-Young problem. Okay, now yesterday we gave some information about Fujita critical exponent, but if we consider the same problem with the forcing term, there will arise differently another critical exponent. And in the next within this presentation, we will discuss about this kind of problems. Yeah, Kobayashi considers this kind of perturbation here, the same equation, but between nonlinearity, they put this kind of Japanese bracket. It means square one plus square root 1 plus x square. And he obtained the following results. Also the same for one-dimensional, two-dimensional case. The critical exponent will be the infinity. And starting with a three-dimensional case, there will be critical exponent represented by this expression here. Differently from the Bendel-Levine-Young results here we have gamma, n plus gamma. If gamma goes to 0, then the critical exponent will be the same with the previous critical exponent. And also in this case, in the subcritical and the critical case, there is no global in time solution. But in the supercritical case, there is global in time solution for sufficiently small initial data. And in 2020, Gileli, Kawakami, and Samet, they consider this kind of perturbation. Instead of source term, they consider source term depending also on the time, but with polynomial type. And the proof here, sigma greater than -1, and it's not equal to 0. And the proof that if sigma is strictly positive, then the critical exponent equals to infinity. There is no global in time solution for NEP. If sigma between -1 and 0, then we have this kind of critical exponent. The critical exponent depends on the sigma. And in this case, in subcritical case, there is no global in time solution, but with supercritical and critical case, there exists global in time positive solution for sufficiently small initial data. It's also surprisingly, because if we put here some time-dependent function, then in this case, the critical case will belong to the global existence case. And recently, Chinese mathematicians Sun, Liu, and Li, they consider this kind of extension. They combine the problem considered by Kobayashi and the previous guys. And they obtain the same results, almost the same results. Here a little bit difference, only the critical exponents. It depends on the gamma and on the sigma. And in this case also, the critical case, in the critical case, there exists global in time solution for sufficiently small initial data. Okay, now, yeah, in 2021, Arabic mathematicians considered Cazenavi-Dickstein-Whistler type perturbation of the previous problem. They consider this kind of problem. Here we have non-local source this integral defined by this expression. This calls Riemann-Liouville fractional integral of order gamma. It was first time introduced by Bernhard Riemann and later by Liouville. And if gamma goes to 0, we say that this integral operator goes to identical operator, like this. And in this case, they prove that if this function, integral of this function is strictly positive, and initial data is non-negative, then there is no global in time solution for any p. Okay, and now let us move to another type of equation, Sobolev type equation, and it's also called pseudo-parabolic equation. It's very popular in the post-Soviet Union countries. Let us consider this kind of equation given by the formula 7. And the first time it was considered by Kaikina, Naumkin, Shishmaryov in 2005. They prove that for this problem, the critical exponent is the same as the Fujita critical exponent. And later, this Chinese mathematician also considers the same problem, and they have a little bit improvement of the previous result. And in 2020, also Chinese mathematician Zhou consider pseudo-parabolic equation with forcing term. And they also have the very similar results as a Bendel-Levine-Junk. If P between this range, since there is no global in time solution for this kind of forcing terms. And if P greater than this number, then there is global solution for some initial and forcing terms. And but in this paper, the critical case was left open. He cannot prove this part. And now let us consider the little bit general case of this equation. Here we just have this integral term. But if gamma goes to 0, we have the same problem as the previous one. And we are interested in the two cases. First one, when gamma between 0 and 1. And second one, when gamma equals to 0, but P is a critical case. And first we define we give the definition of a weak solution. We say that U from the space is a global weak solution of our problem if it satisfies this kind of integral identity for all T positive and this kind of smooth functions with compact support. And let us formulate our first results. Suppose that U0 and omega is an integrable function, and the integral of omega is positive. If gamma is strictly positive, then for all any P, there is no global in time solution of the considered problem. From here follows when K equal to 0, if you remember here, K is non-negative. It will be the 0 also. When K equal to 0, then our equation coincides with the classical heat equation. Then our results, these first results, improve the results of these guys. Because here we don't assume any positivity of initial data. And let us give some short proof of this theorem. Yeah, the proof will be by the approach test function. We consider this kind of test function. Here, psi of t can be defined exactly by this. Here, m strictly positive, this number. And psi of x will be defined by this kind of test function. And here, r and t is a quite large number. And suppose that function phi satisfies this kind of property. And using the definition of weak solution, we can get this kind of inequality for the right-hand side. And for the first term, using the epsilon Young inequality, we have this one. And for the another terms, we also get the similar inequality. And here, all first term is the same. And the second one depends only on the test function. Then the expression 9 can be rewritten as formula 10. Here, left side and right-hand side does not depend on the u. It depends only on the test function and the initial function and the forcing term. Here, E1, E2, and E3 can be defined by this expression. And now we will estimate these three integrals, E1, E2, and E3. For a time-dependent function, we have this kind of calculation. And then changing the variables by space variable. For integrals E1, E2, and E3, we have this kind of estimates given by the formula 12. And here, and also this integral can be estimated as this one. And combining the above calculations, we have this kind of inequality. Here, right-hand side depends only on capital T and capital R. And the left-hand side depends only on the forcing term and the initial function and test function also. Here, if we fix R and capital T goes to infinity, then the right-hand side of this inequality goes to 0. And this is a contradiction with our assumption, because this function will be non-positive. And then let us give our second result about critical nonlinearity case. And we also suppose that U0 from L1 space, and this forcing term satisfies this kind of condition. And if P is critical, then the solution of this problem does not admit global in-time solution. There is only blow-up solution. And this gives us answer to the Joe's question, open question. And also, here we don't assume any additional restriction for the forcing term. Then, in the case of k equal to 0, our results improve the results by Bendel, Levine, Jung classical paper published in 2000. And let us give the proof of this statement. Yes. Okay. Let us consider also this kind of test function. Here, novelty of this approach, we choose another type of test function by the space, logarithmic with a logarithmic argument. for this logarithmic argument test function, we assume this kind of restrictions. Then repeating the same calculations as the previous case, we have for I1, I2, and I3, we have this kind of inequality. Finally, we have this one. And here, instead of capital T, we put R power G. And if G greater than 2, we have this one. Then all power of this R and logarithmic R will be the negative. Then here we can get the limit, R goes to infinity, and also the right-hand side will be equal to 0, which gives us the contradiction. And this is proof or theorem. And now let us give some recent results on this direction. In recently, 2024, these Chinese mathematicians considers this kind of generalization of the previous problem, and they prove this kind of results, but they have only blow-up results for subcritical case. And also, Majdub in the 2023 consider fractional power space fractional case of this problem, and also here some singular coefficient. And he proved this kind of critical exponent. The critical exponent here depends on S, N, and sigma. And one of the last results, we extend together with Michael Rozhansky and Mirkhan Burhanov, we extended the Bendel, Levine, Janks results to the Heisenberg group, and we obtain this kind of critical exponent. Here, Q is a non-homogeneous, homogeneous dimension of Heisenberg group. Yeah, it was a last page of my presentation. Thank you for your attention.
I just want to ask, for example, this equation or this one.
Okay.
There are many different equations. And they still have some physical interpretation.
Yeah, that's a good question. In general, yes, but in this case, I don't know, because if you consider some equation with this part, there is some application in physics. For example, Benjamin Bona-Mahoney equation comes from this kind of linear part, this kind of equation. But exactly about this equation, I don't know. This is purely mathematical.
Thank you.
Thank you.
Yes.